But essentially, the actual optimization backprop is just the means by which you get the gradient for gradient descent. And so now, if you're someone developing new hardware, especially particularly something with any analog components in it, you have to ask yourself, well, I might not be able to do backprop very well because I don't have a perfect model of my hardware. Is there another way I can get the gradient? And the answer is yes. This has actually been well known for a while. You can use perturbative methods. They're very universal, sometimes called zero-order optimizations or model-free methods. And essentially, the easiest way for me to get the gradient, and I'll just tell you right now, I can tell you the algorithm, is look at your parameters, in this case, some weights of a neural network, say, and wiggle them a little bit, right? So maybe I have a weight W, I change it by delta W, and then I can observe the change in my cost on the output. I get some delta C. And from that, I can tell you the partial gradient of that weight. Now, if I do this, I have to store, I have to do one at a time, and I kind of have to store them in memory, and then I calculate the gradient, and it's kind of inefficient. And so some people in the early 90s and late 80s figured out some nicer techniques of, well, maybe I can do everything at the same time. So instead of wiggling one weight at a time, why don't I try wiggling all of them? And I'm going to show you this to you in sinusoids because it's a little bit easier conceptually to understand. And essentially what you do is you take each of your weights. You say, I have a weight 1, weight 2, weight 3, and I'm going to apply a 1 megahertz perturbation to weight 1, 2 megahertz perturbation to weight 3, 3 megahertz to weight 3, and so on and so forth. And what I'll end up with is actually each of those perturbations at those different frequencies will have a corresponding output of the modulation of the cost. So the cost will have a 1 megahertz term, a 2 megahertz term, a 3 megahertz term, and so on and so forth. And all I need to do to extract the partial gradient for any single weight is just to integrate it for a little bit of time, and then I will derive like dc dw. All right. So in an actual, if you had a little piece of hardware, again, I'm not making any specifications on what that hardware looks like. I'm not talking about any topology in particular or activation functions in particular. This is very, very general. It's a black box approach, right? I produce different modulations on each of these weights. And on my cost, again, I get these different modulations that correspond to the delta C's of each weight. And from that, I can extract the entire gradient of your system in a single go if I just sit there and integrate for a little while. And the longer I integrate, generally the better the approximation of the gradient will be, and so on and so forth. Now, I've shown you this with sinusoids, but actually this is just more generally the truth than that. Anything that's orthogonal or even quasi-orthogonal can be done this way. So I don't have to put sinusoids in on my weights. I can just say, let me do plus epsilon to some weights and minus epsilon to other weights in some random pattern. And that's statistically orthogonal enough that I can actually extract out this same gradient. Again, without doing anything, without knowing the specifics of my hardware or anything like that. In fact, you can even use noise sources as long as they're uncorrelated to derive the gradient out of a physical system. So just to sort of prove this point, my colleagues and I have been putting together sort of a set of simulations, and we essentially wanted to show, we're claiming we can compute the gradient. Can we actually compute the gradient? And we just have a very simple toy problem, like a 2-bit parity XOR thing, and we measure the gradient. We do some weight updates, just like backprop, and we see that in this simple example, it kind of follows the same curve. It's a nice sort of proof of concept that you can walk downhill using gradient descent on an arbitrary on an arbitrary network, right? And what's nice about this, again, is there's no knowledge. It's model-free. There's no knowledge of network architecture or parameters or anything like that. All you need to be able to do is run inference and perturb your parameters. As long as you can do those things, you can optimize your hardware. And actually, what's really interesting more than anything else is, like I said, a lot of this stuff kind of came out in the late 80s or early 90s. And so there are a bunch of convergence theorems, mathematical proofs, this and that, and there's been a few, hardware VLSI things, but most of those demonstrations have kind of been at the 6 neuron level or the 20 neuron level or something. They've been kind of small scale, just as a proof of concept to show that it actually works. But what's really neat is that if you actually go and you do this computation, say I take CIFAR10, right, with small network, 26,000 parameters. If I run that on a NVIDIA 1080, it takes about 500 seconds to get my backprop trained to a certain level. And if I just run this perturbation, I might have to run through lots and lots of iterations of doing these perturbations, right? But if I'm operating even at a what I consider to be a very marginal operating speed of 1 megahertz, I can solve this CIFAR10 at the same level backprop did in about 10 seconds. Not down from 500 seconds, like almost an order of magnitude and a half, essentially. And so the notion here is that you take your hardware, which might be very energy efficient, very fast, but you don't know exactly how to get it right. And you can apply these perturbative methods and actually solve useful and have it produce useful output. So the next thing we kind of went and looked at is areas that didn't really have as many convergence proofs and mathematical theorems behind them, and said, well, if you've got a piece of hardware, especially something that has analog in it, you have to deal with noise. That's the first thing that's going to start killing you, right? Well, what happens if there's noise on the cost output? I've got a laser coming out of this thing, right? And it's got some Gaussian noise on it. Or what happens if my weight updates are not quite deterministic? I tried to tried to add 0.7 to my weight, and instead I got 0.3. Or what happens if my activation functions are not modeled quite the way I thought it would? There's a spread of them. And essentially what we found in all of these circumstances, you can still train your device, and you can still get as good as you got before if you're just waiting to train for a little bit longer. So effectively, noise is one of these things that just hurts your training time, but does not kill your operation, which again, for emerging hardware and for anything with an analog component to it is very promising. And so we kind of looked at that and we asked ourselves, well, what about quantization, right? So let's say I have, in one example, let's say I want to train using these model-free techniques directly on quantized hardware. Well, maybe I have a memristor that's sort of hard to model properly, right? So I'm lacking a simulation or model, so I can't use backprop. Or I have an edge device that, I want to do some, continual learning on somewhere down the road. It's very unlikely I'm going to put backprop directly on that chip remotely, but I might be able to perturb the parameters remotely and actually produce some useful updates. And essentially what we found here was that when you're training these quantized circuits, if you have a fixed duration, say I train for some number of time steps, in this case 10 to the 7 time steps, high bit depths, you get good accuracies. And as you drop the bit depth, if I train for that fixed amount of time, it starts to suffer, as one might expect, right? But what's interesting here is that you can actually recover all of that again in the same way we could recover it with noise. As the bit depth drops, you just increase your training time by a factor of 2, by a factor of 5, by a factor of 10. And this 10 to the 7 iterations thing might be kind of scary because you're thinking of your normal operation. But again, if you're operating even at a megahertz, that's 10 seconds. This is not much, actually. The other thing that we looked at as well was correcting quantization errors, errors in quantization, where say you had a magnetic tunnel junction that has a continuum of values that can essentially take, but you say it's quantized to 4 bits because in reality, when you try to write to that device, you're just going to get it, you can't get it that accurate. And so you just have to bin it kind of, right? Well, what happens in those circumstances is what you might do is you might say, okay, I've got a pretty good idea of what my model is. Let me train it with backprop to the best of my ability. Now I'm going to transfer it to my hardware. Whoops, for theta I tried to write a 7 and actually it came out as a 4 when I actually applied my write operation. What do I do at that point? Well, actually you can use this sort of MGD framework with these model-free techniques to drop you right back down into that nice local minima of the cost. And so what we did was we simulated this on a data set using a 4944 dense network. It's just a fairly simple one that's easy to run fast. And we showed essentially that you could do this kind of retuning process where we trained, essentially what we did was we performed back propagation. We got the problem to 100% accuracy. And then we performed what we call an imperfect transfer, right? There's a 10%, I tried to write the weight, but it was off by 10%, or it was off by 20%, it was off by 30%, right? And as you can see from this blue line, okay, your accuracy starts to suffer as you have larger and larger deviations from what backprop told you to do from when you wrote it to the actual device. Now, fortunately, you're operating in a continuum with your analog MTJ in this case, right? So you can actually use MGD, these model-free methods, to look at your hardware, to actually ask your hardware, don't tell me where you think you are, run where you actually are. I'm going to perturb you a little bit, and I'm going to find your gradient. I don't care what my model says. I want to know where you actually are, and I want to minimize you even further. And so what we were able to do is basically show that through this perturbative technique, we're able to basically bring it back to like 100% accuracy, just after that erroneous transfer. So again, this is a quick talk, but I just wanted to point out, so these techniques, what we call multiplex gradient descent, because you don't have this multiplex signal, it's just a framework wrapping a lot of techniques that have been shown theoretically in the past. They're very resilient to noise and imperfections. They can be used to either train things directly or to fine-tune things. And most importantly, we're actually really interested in helping train your hardware. So if you have a very difficult, uncooperative piece of hardware, we would love to hear from you.